Hello, my name is Ari Morcos. I'm a research scientist at Facebook AI Research, and today it's my pleasure to present this position talk encouraging more falsifiability and interpretability research. Before I get started, I want to thank the organizer, Bole, for inviting me to give this talk, and thank Matthew Levitt, a former Facebook AI resident who's worked with me a lot on these topics and with whom I co-authored the position paper upon which this talk is based. So interpretability can be viewed as building human intuition and understanding for complex black box models. But while intuition is critical for understanding, and verified intuition can be misleading and in many cases lead us astray. Now, in order to verify an intuition, it must be falsifiable, as eloquently put by Karl Popper over 60 years ago. Quote, "Insofar as a scientific statement speaks about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality." Now, in many ways, this statement might seem trite or obvious. Of course, science should be falsifiable. That's what we're taught, from the very first days of our scientific training. But making truly falsifiable statements is often easier said than done. And many intuitions, which can seem rock solid, can actually be very misleading. So as an example, consider the beloved Gaussian. We're all familiar with the classic bell curve of a one-dimensional Gaussian. In this case, of unit norm. Most of the mass is focused at the center, at the mean, at 0 in this case. And we have this nice clear fall off as we move away from the origin. If we now imagine extrapolating the intuition we have from the 1D Gaussian to a 2D Gaussian, it makes a lot of sense. The 2D Gaussian looks very similar to the 1D Gaussian. Again, most of the mass is at the origin, and as we move away from the origin, the density is going to fall off in this nice bell curve sort of fashion, and instead of just doing this along one dimension, now I'll do it along every dimension in 360 degrees, so we get this bell-shaped object. So we might think if we extrapolate this to even higher dimensional spaces, say 1,000 or a 10,000 dimensional space, we'll see something similar. We'll see that most of the density is at the origin, and then as we move away from the origin, the density is going to fall off following this Gaussian shape. So we might imagine, for example, in high dimensions, we might imagine something where we kind of have this high dimensional sphere where it's really dense in the center and it gets kind of less and less dense as we move away from the origin. However, it turns out this isn't what high-dimensional Gaussians look like at all. High-dimensional Gaussians are actually much more similar to soap bubbles, where there's almost no mass in the center, with the exception of at the exact origin, there's infinite density. But almost all of the mass is concentrated at the edges on the soap bubble. And if we were to take the norm of samples drawn from this 10,000 dimensional Gaussian, we'll see that the norms are going to be on average about 100 with pretty low variance, which in this case is just a square root of the dimensionality. So this I think, is a really clean example of a distribution that feels intuitive, that we think we understand, but if we take that intuition that we've drawn from these low dimensional settings, which makes sense to us as humans, and try to extrapolate them to these high dimensional settings, we can be led really far astray and draw conclusions about what this high-dimensional space might look like that aren't going to be true at all. If you're interested in a more description of this, Frank Huzar has a really wonderful blog post going through what Gaussians look like in high dimensionality. So in a lot of ML, we try to build intuition for high-dimensional spaces by thinking about lower dimensional spaces. So just some examples. For example, one big one is t-SNE, which is a method of dimensionality reduction that's become really popular, a nonlinear dimensionality reduction. Here, for example, is a plot from the original DQN paper in Nature in 2015, where they took all the different states of the agent and they used t-SNE to collapse this high-dimensional state space into a small kind of 2D dimensional state space, and then look at kind of clusters of game states and space invaders corresponding to clusters in this t-SNE space. So this is a visualization that is designed to give us intuition about what the model is doing and what the different states are. As another example is the realm of methods that are aimed to give us attribution or saliency maps for images, which basically try to say what are the parts of the input that were important for a given network's decision. Here's another example where that was applied to RL, in this case Enduro and Atari, where they're looking at, okay, the value network seems to be focusing on the road ahead. So that seems to give me an intuition that this network is doing what I think it should be doing. That's how a human would solve this task, so it's good that it's looking at the road ahead. And this again takes this high-dimensional system that lives in this kind of high-dimensional space and puts it into a lower dimensional space that makes sense to us, in this case images. We understand as humans how to interpret images. And another example of visualization is visualization designed to explain the activity of single neurons. So for example, here's a case of a language model in which they found a neuron which was sensitive to the position in line. It seemed to fire more at the beginning of lines than at the ends of lines. And another one, for example, that turned on only inside quotes. An alternative approach, instead of just looking for neurons and seeing what they respond to, is to take a given neuron and say, hey, let me make the optimal stimulus for that neuron. And then if by looking at that stimulus, maybe I can understand what's going on. So there are tons of these approaches in machine learning that are based off of visualization. And I'm going to argue that basically these are all non-falsifiable in at least the way that they're generally presented, in that by putting more work into falsifying many of the claims, or to trying to make claims that can be falsified in these settings, we can move towards better, more verified, truer statements about how our models are working. So as a quick outline of the talk, I'm going to first talk about several impediments to falsifiability and interpretability research, and then I'll talk about 2 case studies of situations in which the field has kind of really jumped onto a given topic that seems to build intuition, and then a lot of more careful work that maybe came later showed that some of the assumptions that were made and some of the hopes of these methods aren't necessarily true. And finally, I'm going to talk about how we can build better hypotheses so that we can really ground our research in falsifiability. So our goal with this talk is really to build intuition so that we can better understand DNNs, but ensure that this intuition is grounded in rigorous, falsifiable experiments. Intuition is a good thing. It's critical. We need intuition, but unverified intuition is where we get into trouble. So let's start with the impediments. So the first impediment that I think is extremely common in interpretability research is simply the underemphasis on clear, specific, testable, and most critically, falsifiable hypotheses. If you don't state a clear hypothesis at the beginning of an experiment, a lot of the time we simply default to weak or not very strong hypotheses, like is something present, rather than asking more important questions like how does the presence of something relate to an aspect of network function. A second important one, and that goes right into what I was saying, is that interpretability methods are often not actually verified as being important for network function. So oftentimes we simply make observational statements or correlative statements, but we don't actually test the causality of the observations that we're making. If we made a certain observation about network function, is that observation actually important for the network's output, or is it irrelevant for the network's output? The next impediment is what I like to call the double-edged sword of visualization. Visualization is a really useful tool, and I don't want this talk to be misinterpreted as my stating that visualization is not useful or shouldn't be widely used. It absolutely should be. It can be extremely helpful for building understanding, especially during exploration. However, it can also lead to strong feelings of comprehension, regardless of how accurate the underlying visualization might be. And this is especially a problem because visualizations are so often based off of individual examples. For example, the plots I showed earlier, which show kind of 1 or 2 frames from an Atari game and say, hey, here's what the network was doing or paying attention to during this task. So it's generally not aggregated across all the examples. And this leads to kind of the lack of quantification. And this is a problem, especially in deep learning, because similar models can have dramatically different properties across different hyperparameters. This is also a problem for interpretability research in particular, because we don't have ground truth in the most cases for interpretability research. We don't know what the models are doing, and in many cases, we're trying to ask questions like, hey, is this model solving the task in the same way that I as a human might solve the task? That's why we like it when we see that a model seems to be focusing on the cat in the image when it calls it a cat. That seems to line up with how I as a human would solve this task. And in many ways, that means that we're really susceptible to confirmation bias, and that visualization can in some ways serve as a Rorschach test for a researcher, where you can see whatever you want to see in the visualization, especially when you're limited to a subset of visualizations, which may be cherry-picked, even unintentionally. Finally, many interpretability methods are designed with the intent to provide actionable explanations to humans. And if this is the case, it's really critical that we conduct controlled experiments to evaluate whether these methods actually bring utility to humans in ways that are actionable. Okay, so now that we've kind of gone through these 5 impediments, let's talk about 2 case studies in which the downsides of the lack of falsifiability have kind of become clear over the course of multiple years. So the first case study I'm going to focus on is what we call the misdirection of saliency, really looking into the story of kind of how saliency has evolved over the last 5 to 10 years. So what is saliency, or attribution maps, or feature attribution visualizations? In case you're unfamiliar, saliency basically tries to address this question of asking which portions of the input are most responsible for a given classification decision. So basically, for example, I have some image classification model, and I want to understand which parts of the image resulted in that model calling it a cat. And typically, these are based off of some form or variation of the gradient of a given output with respect to the input. So typically, we're looking at how would the model's output change if I change this input. And these might often look like this. This is from the original introduction of these in the deep learning context, where you can see, for example, for the dog, up here, the saliency map underneath seems to generally highlight the location of the dog and not highlight the dirt. Similarly, for the fruit, we see that the fruit seems to be more highlighted than the hand or than the background of the image. And the reason that saliency maps are intuitive and are helpful is that, again, they take this high-dimensional space. How is this model with millions of parameters functioning? And it puts it into a space which we as humans can easily understand, which is images. I understand images. I know how to interpret them, even though they're complicated. I don't really know how to interpret a million or 10 million, or in the case of some recent large transformer models, maybe billion or even getting up to trillion parameters. How do I think about a billion-dimensional space? It's not clear, but it's much easier to think about image space. I understand image space as a human. Now, you might notice that these saliency maps that come out they're kind of hard to interpret. So there have been a lot of work in subsequent years to improve these saliency maps, to make them easier to interpret. For example, GradCam was a method from several years ago which tried to discriminate between which portions of the image are responsible for which outputs. So in this case, they can kind of look at, okay, well, what are the parts of the image that are responsible for the cat or the dog classification? And you can see that these get much nicer in many ways. These are not just using the vanilla gradient, they're using some combination of the gradient and other approaches. Or here's another example, SmoothGrad, which is compared to a couple other methods here, which tries to remove some of the noise from these saliency maps. As you can see, that many of the vanilla saliency maps tend to be quite noisy. So the goal with SmoothGrad, is to highlight the portions of the image that are really critically important. And these are just 2 of many methods. There have been many saliency methods. Especially there was a period, in 2016, 2017, where many interpretability papers were introducing new approaches to saliency. And saliency has been widely used as a result. Because it provides this seeming intuition, it's been used in a lot of settings. In addition to image classification and supervised learning, it's been used extensively in RL. So for example, here's a paper from ICML a couple years ago that tried to debug models by looking at cases where they're not looking at the right things. For example, in Miss Pac-Man, the Pac-Man character, Miss Pac-Man almost dies here, I think, shortly thereafter, and because it gets killed by this red ghost, and yet the model, it doesn't seem to be attending to the red ghost. Or similarly, in Frostbite, the agent has to jump between these platforms. The agent should be looking at this circled platform, which is a destination platform, but the model doesn't seem to be paying attention to it. So this is used in this context as a debugging tool to say, okay, our model's not really performing the way that we want it to. Why is that? Maybe it's not attending to the right portions of the image or not acting the way that we as a human would expect this model to act. And it's also been applied to other aspects of RL. For example, in a recent paper, it was applied to Go, using it to try to figure out which portions, which pieces in particular are most important for a given action. But saliency hasn't just been used in the context of basic machine learning research. It's also been used in applied settings, including some safety critical ones like medical imaging. So, for example, here's a paper from several years ago that tried to detect pneumonia from chest x-rays. Excuse me. And in addition to outputting a prediction with some confidence about whether or not the patient is positive for pneumonia, this system would also output a saliency map, which would allow the doctor who would be receiving this report to try to determine whether or not they trust this model. Say, okay, well, this model said that the patient has pneumonia because of this blotch that's in this specific spot of their thoracic cavity. Similarly, it's been used recently for interpreting knee MRIs, and even more recently for detecting anemia from retinal fundus images. There are tons of papers that are applying saliency to various medical imaging settings to try to design systems that provide explanations to doctors so that they can better use these models. Now, since these things have been used so widely, since saliency has been used so widely, a lot of folks in the community have started taking a more critical eye to these methods and asking, how do we tell whether what this saliency method is telling me is actually true? What are the sanity checks that we can do to make sure that this is true? And this is, again, a real problem because we don't have ground truth generally. I don't know how the model is working to begin with, so it's not clear whether the method I'm seeing is actually revealing something that actually reflects the underlying methodology of the model. So in a recent paper from a couple years ago, that was at ICML, that introduced integrated gradients, the authors proposed two axioms that saliency methods should satisfy. The first axiom was sensitivity, and this is a really basic idea. It's basically that if two inputs differ in only one feature, but they result in different predictions, then the saliency map should also be different. Then the differing feature should have non-zero saliency. Then the differing feature should be clear, should put emphasis on that single feature that differs. You can think about this as basically saying that if I have two inputs that are otherwise identical, but they result in different outputs, whatever is different about them has to matter. So the saliency method should show me that it matters. But as the authors show, it turns out that standard gradient-based saliency actually fails this axiom because ReLUs can result in zero gradients even if you have different inputs if the pre-ReLU activation is less than zero. It's in that flat regime of that activation function. So in some cases, even the most simple, straightforward approach of just using gradients would actually fail this pretty straightforward axiom. It means that we'd end up with a lot of false negatives. The second axiom that they introduce is what they call implementation invariants, which is the idea that if two networks are functionally equivalent, and what we mean by functionally equivalent is that they compute the exact same function, which means their input-output map would be identical across all inputs. So if that's the case, then they should have identical saliency maps as well, right? If they compute the same function, it shouldn't matter whether it's implemented as a transformer or as a COMNet or as an MLP or even as a non-neural network model. The saliency map should be the same so long as the function that's being computed by that model is the same. So in other words, the saliency map should be invariant to the implementation of the function. And this is actually one that standard gradient-based saliency does satisfy, but many of the more complicated saliency methods do not. So motivated by these two axioms, the authors propose a new method, integrated gradients, which satisfies both these axioms and seems to provide, nice saliency maps. They show that it seems to be better than using vanilla gradients in the image classification context over here, and in medical imaging, it seems to do a good job of picking out lesions, in this retinal scan. However, follow-up work went on to find some issues with integrated gradients by introducing a new axiom, which the authors in this case called input invariance. And this is the idea that if you apply a constant shift to all the elements of an input, the attribution method should not change. The map should be the same. So as an example, we can take an MNIST classifier here and simply just subtract 1 from all the pixels. And if we take vanilla gradients, you can see that the saliency map dramatically changes. And even if we look at more fancy methods like integrated gradients here, in many cases, it depends on kind of how you use the method. Depending on what you set as a reference point, it might work if you reference to black, but if you reference to the value 0, then this is going to completely break everything. And this kind of goes to show that even for these methods that are a little bit smarter, you still have to be really careful about how you use it. And it turns out that even if you're careful, that might not always work. So they have this nice catastrophic attribution failure where they simply take MNIST images and they add a constant shift, this little image of a cat, this hand-drawn image of a cat. And you can see that despite the fact that this cat is added to every single input in the data set, it does not change the classification decision in any way, shape, or form. It does not impact what information is present in the images. All of the saliency methods focus tremendously on the cat, much more than they do on the digit, even the fancy new ones like integrated gradients. So here's another case where we find kind of a sanity check that these methods should be following, and yet they're not. Finally, in a really beautiful paper, Julius Adebayo and his colleagues started with this observation that many saliency methods seem to be very similar to edge detectors. What I mean by that is this here is just if you take a standard edge detector and you just apply it to these images, here's what you get. This was not put through a network. This is just based off of the input data itself, and that has nothing to do with the label. It's unsupervised, this edge detector. You're just taking a simple edge detector. And if you compare that to all these different saliency methods, you'll see that for many of them, they actually look really similar to this edge detector, with the notable exception of the gradient space methods, or the pure gradient methods. So motivated by this observation, Adebayo and colleagues proposed these two randomization tests. The first one being the model parameter randomization test, which is based on this idea that if a saliency method depends on the learned parameters of the model, then the saliency maps for a randomly initialized untrained network should be different from the trained network, basically saying that the point of our saliency methods is for them to tell us something about the model, not about the data, but about kind of how is my model solving this task. So if I completely reinitialize my model, now I have a totally different model, the saliency map should change. So the way that they tested that is by taking the saliency maps for a number of different methods and looking at what they looked like, and then progressively randomizing from top to bottom more and more and more of the network. So they basically just reinitialize all the parameters eventually in all of the layers. And that's what's shown here as we go across the right. And what you'll notice is that for many of these methods, the saliency maps do not change even if the entire network is reinitialized. For example, guided backprop shows nearly identical saliency maps, even when the entire network is randomly reinitialized, which really tells us that the models, saliency maps that we're getting, do not depend on the model parameters themselves. Now, as I mentioned, we always want to be quantifying things, and Adebayo and colleagues did exactly that. So instead of just showing this visualization, they tried to quantify this by measuring the rank correlation between the original network and the original map and the maps when you randomize more and more of the network. And what they find is that, for all of these methods, it's substantially above above 0, which is chance, even when the entire network is randomly reinitialized. And for some of these methods, like guided GrabCam and guided backprop, it's fixed at 1, basically, even once the whole network is reinitialized, the saliency map doesn't change at all. So this is obviously fairly concerning. Another randomization test that they tried is what they call data randomization, which is based on this idea that if a saliency method depends on the data labels, i.e. P of y given x, then the saliency maps for a model trained on data with different labels, with randomly permuted labels, should be different from the maps generated against the uncorrected data set. Same idea. If I change the labeling function for this data set, then saliency should function differently. But it turns out here again, if we compare the true labels case to the random labels case, we find that for many of the methods, the saliency maps are identical, again with the notable exception of vanilla gradients. which, as we know, unfortunately fails some of the tests that integrated gradients propose, primarily sensitivity. And again, they quantified this and found that the correlations were significantly above 0 for the majority of these methods. Finally, in the last part of this case study, I want to talk about whether saliency maps actually help humans to predict what a DNN is going to do. This is their stated goal. And in a really nice study from several years ago from Chandra Sekaran and colleagues, they trained humans with this instant feedback model, basically, to try to predict whether a VQA model is going to correctly output its choices, its answers to questions. And then they provided the humans either just with feedback and nothing else, just the input, or with various other factors. For example, the GradCam map, the top 5 prediction confidences, or just a standard saliency qualitative attention map. And notably, what they found was that providing humans with this extra information made no difference in the human's ability to predict the output of the VQA model. And in fact, providing the qualitative attention map seemed to, if anything, decrease performance, although this doesn't seem statistically significant. So this seems to suggest that these methods, these saliency methods, aren't actually helping humans to better predict what's happening with the model. However, another study more recently looked at a similar task, except in the context of image classification, and did find that saliency made a difference, although the difference was very small. It was only about a 5 or 6% difference in performance, which is barely significant. But they did find that if there may be a difference here, but it's very small. If it is, it's definitely not helping humans tremendously with respect to predicting the outputs of these models. So what are the takeaways from this study, from this case study? First off, saliency maps and attribution maps, they generate these intuitive and visually appealing annotations, which at first they seem to explain why a network made a particular decision, and that seems really useful for a lot of contexts. But unfortunately, many of these methods fail these critical sanity checks. Most notably, and most importantly, many of these methods don't depend on the learned function of the model at all, but just they depend on the data. Which means they'll produce the same outputs no matter how the model is solving the task, which is obviously not going to do what we want if our goal is to understand why a model is making a particular decision. And these flaws, I think, can be especially concerning given that saliency methods are being used in safety-critical settings like medical imaging and are still being used even though some of these studies are several years old. Okay, so that sums up the case study on saliency. Now I'm going to move on to our second case study, which focuses on understanding networks through easy-to-interpret neurons. So the idea of looking for kind of individually interpretable neurons which seem to line up with some task feature has a long and storied history in neuroscience, which is where I was trained. Going all the way back to the 1950s with Horace Barlow looking at the response of retinal cells to different light signals. And they found units which seem to prefer very specific patterns of light. Going from very simple stimuli like that to very complex stimuli, in the mid-2000s, Kian Quiroga and colleagues found in macaque medial temporal lobe these Jennifer Aniston neurons, these neurons which seem to preferentially and exclusively fire in response to images of Jennifer Aniston. They also found Halle Berry neurons and Kobe neurons and all sorts of neurons that seem to be very selective for an individual person's face, regardless of the context in which that face is presented. So this very much seems to suggest, hey, maybe if we just understand these individual neurons, we can really understand how the brain is working. Now, this same sort of approach has been used extensively in deep learning, going back to the beginning of the modern deep learning revolution, in 2011, where Kwok Lee and folks and colleagues, found these face neurons popping out of unsupervised models, neurons which in red is responses to face images, and in blue non-face images, and they found this kind of clear difference. These have also been used in the context of analyzing language models. I already presented this, but showing that kind of here are cells which seem to be very responsive to the line position or to quotes. And a recent example which got a lot of attention was OpenAI's sentiment neuron, where they trained an unsupervised language model and found that there was an individual neuron which was extremely selective for sentiment. It was only active for the most part in response to positive reviews rather than negative reviews. This is just one approach to understanding individual neurons. Another one is activation maximization, this idea of trying to find the optimal input for a given unit. And then by looking at that input, that might help us to understand what's happening in this case and how this model is working. So one example of that is channel attribution, or another versions use kind of more complicated things like GANs to generate even better, more interpretable inputs for these units. However, despite their use in deep learning and their original use in neuroscience, there's been a real shift in neuroscience from single units to populations. For example, here's a paper from several years ago from one of my former lab mates, which showed that basically no matter which brain area you look at in posterior cortex, you find that there are lots of neurons which seem to like everything, which really seems to argue that no matter where you look in cortex, you will find units which seem to be selective. So selectivity seems to be very widespread. But more importantly than that, even if you take this kind of widespread selectivity for everything, where the signal just seems to be there everywhere no matter what, whether or not it's relevant, it turns out that a lot of these non-selective neurons contribute to population coding. And there have been some really nice studies across a number of different model organisms showing that if you just look at the units which are not easy to interpret, there's actually tons of information present there, and that those units actually may be more important than the selective units. And in general, there's been this really movement towards population-level phenomena for characterizing neural systems away from individual neurons. And a lot of the reason that neuroscience has focused on individual neurons is for technical reasons. Up until about 15, 20 years ago, it was very hard to record from more than one neuron. Now we have the capability to record from hundreds or thousands, or in some cases even tens of thousands of neurons simultaneously, and that's enabled this shift from looking at individual neurons to looking at these larger populations and these distributed representations that underlie neural representations. So this brings us to a paper that I worked on several years ago that tried to kind of address whether or not these single units that are selective actually matter. So the previous studies I talked about mostly showed that these individually interpretable single units existed, that they're present, they found them. But it didn't actually test whether these units causally lead to better performance. Are they necessary? Does having more selective units make your model better? Does having more selective units make your model worse? Is selectivity a good thing for network function? To test this, we performed a pretty simple experiment where we went and we ablated each neuron, which means we just deleted it or forced its activation to 0, and then measured how the network's loss changed after that ablation. If a unit's really important, we would expect that the loss would go up a lot when you delete it. When you get rid of that unit, the loss gets much worse. If these selective units are more important, we'd expect that the more selective the unit is, the greater the impact of deleting it. So we'd expect to see a positive correlation. In contrast, we actually observed this negative correlation where the more selective the unit was, the smaller the impact on the loss was. And the less selective a unit was, the higher the impact on the loss was. And it turns out that this is mostly driven by really important non-selective units in early layers where they shouldn't be selective for individual classes. We saw a similar phenomenon in the context of an ImageNet trained model on ResNet. Sorry, this on the left is a CFAR trained model. This is a ResNet trained model, ResNet on ImageNet trained model, where we see the same effect that for the most part, no matter what your selectivity is, your impact's not going to be very strong unless if it's very low. Now, this result wasn't without controversy. After we published this paper, a nice paper came out from Bole, who you'll hear from in this tutorial, analyzing what happens when we ablate these units. And what they found was that, well, yes, when you ablate individual units, you might not have this relationship. Sometimes you do actually have this really strong drop in performance for ablating selective units for individual classes, not aggregated across classes, but for individual classes. Although interestingly and kind of surprisingly, sometimes you might ablate a unit which is selective for one class, and that will result in a really strong deficit for an entirely different class. So the class that was most harmed by ablating a unit was not always, and in many cases actually was, different from the preferred class of the unit that was ablated. So this seems to go in the other direction, suggesting that, hey, actually maybe these class selective neurons are really important. As another example, there's a recent paper analyzing that sentiment neuron I mentioned, and they tried deleting it, and they actually found that, of all things, it increased performance ever so slightly, by a very small amount, when you delete this neuron. So if nothing else, that neuron is definitely not necessary, and maybe even is a tiny bit harmful to performance. And if you compare it to ablating a bunch of other random neurons, you find that the majority of neurons actually result in a slight decrease in performance. Whereas, deleting the sentiment neuron produced this slight increase in performance. Now, the problem with all of these studies that I just talked about is that they're, for the most part, all post hoc. They take a model that's already been trained, and then they go and they delete something and they say what's happened. And that doesn't necessarily make strong conclusions for a number of reasons. For example, in the study that I presented, in the study that I did, where we tried deleting neurons and seeing what effect that had, it could be that the reason that the selective neurons weren't as important was because there are a lot of them and they're redundant. So maybe when I delete one, there's just another one that's right there ready to take its place, so it doesn't have a negative impact on the model, but it's still actually really important if I deleted all of those neurons. To try to get around that, in a follow-up study that was led by Matthew Levitt, we tried to do this not in a post hoc fashion, but during the course of training, and actually retrain models with this restriction added. So we designed a regularizer to either encourage or discourage selectivity, which allows us to manipulate how much selectivity is present in the model and see the impact that has on test performance. What we found was that when we decrease the class selectivity of networks by regularizing against class selectivity, we found that performance actually increases significantly before eventually starting to drop again. And in fact, we can remove or decrease selectivity by over a factor of 3 with minimal change in performance, and we can reduce it by close to a factor of 2 while increasing performance substantially. In contrast, if we instead regularize to increase selectivity and encourage more selectivity, performance immediately starts dropping. So what this suggests is that by default, networks are learning actually a little too much selectivity. They're right on that edge where if they learn any more, their performance is going to drop a lot. But they've already sacrificed this amount of performance, this a couple percent here, by learning a little bit too much selectivity. So this is a little confusing. If selectivity isn't helpful, why are networks learning it? And to be honest, I think that's still a remaining mystery as to what's going on here. However, the story isn't quite so clean, unfortunately, because while this is definitely true for discriminative models, that selectivity doesn't necessarily seem to be causally necessary or sufficient, in generative models we actually see a quite different effect. So for example, here's a really nice paper from David Bao and others from a couple years ago where they took a generative model, used it to generate a lot of images of churches. They identified the units in the GAN that matched trees, and then found that when you ablate those units, you remove most of the trees. And when you activate those units, you add those trees back in. So I think this is a really nice causal test. This is falsifiable, and it does show that these individually interpretable units do play a key role in determining the semantic features of the output. Although I'll note that some follow-up work in rewriting GANs from the same group moved away from individual neurons towards vectors and actual combinations of neurons to manipulate with better fidelity. But the story might be different a little bit in discriminative and generative models when it comes to the importance of these individual units. So what are the takeaways from this case study? First off, the tractability of these low-dimensional signals can really be enticing to researchers to just focus on these individual units and say, okay, I'm only looking at a subset of these units and I'm only looking at one at a time because that's tractable. I can't look at all the units, but I can look at just one. I can understand just one. And that leads people to think, okay, this one unit is representative of the network's behavior. And while that sometimes works, a lot of studies have shown that but through ablation and these class selective regularization, that a lot of the times the properties of individual units aren't actually related to network function in the way that we want, and they don't necessarily reliably extrapolate to thinking about how the full high-dimensional system works. And that what we should really be pushing for are methods which try to understand the networks and utilize functionally and causally relevant properties. And this means you almost have to do retraining of some sort, or at the very least you have to manipulate and perturb networks to try to understand how is this observation I've made about the presence or the existence of something related to the output of the network. And finally, I would say that as researchers, we have to focus on properties that exist across neurons, at these distributed high-dimensional representations, and develop tools to make those properties more tractable and accessible to intuition. We need to get intuition here, but we need to keep our intuition grounded in the actual high-dimensional spaces that these networks live in. Okay, finally, I'd like to end the talk by discussing how can we build better hypotheses and go through an example of several hypotheses of increasing strength and what their various pros and cons are. So as a first hypothesis here, feature selective neurons are the foundation of DNN function. Unfortunately, this hypothesis doesn't have really any pros. It's a pretty bad hypothesis in most ways. It does have a number of cons though. It's not falsifiable. How do I define foundation? How do I actually falsify this? It's not clear what it means for something to be the foundation of DNN function or for something to not be the foundation of DNN function. So foundation is way too vaguely defined here for us to actually design an experiment to test this. There's also no concept of a baseline for comparison, which is really critical. We have to know what's our null hypothesis, what do we expect by chance, and that should be clearly stated within the hypothesis of what is the comparison. So let's make a slightly stronger hypothesis here. If feature selectivity is important for DNN function, then we should find feature selective neurons. So this does have some pros. It's definitely better than the previous one. Most importantly, it's falsifiable. If there are no feature selective neurons, this hypothesis has been proven false. However, that's a little bit challenging because proving the non-existence of something is often really hard. What if you just didn't use the right method to look or weren't looking in the right way? It's much harder to prove a negative than it is to prove a positive. So it's falsifiable, but it's hard to falsify. Another big con here is that it's unclear what we should expect by chance. How many feature selective neurons would we expect if feature selectivity is not important for DNN function, just randomly? Probably there should be some just by random chance. So how do we gauge that, and how do we decide whether or not an effect that we see is indicating a real signal or instead is just noise that is present by chance? And finally, this hypothesis actually has a fundamental causality problem here, which is that the statement itself wouldn't even be true, which is that the presence of feature selective neurons does not necessarily imply their functional importance. So it is true that if feature selectivity is important, we should find them, but just because we find feature selective neurons, it doesn't mean that feature selectivity is important for DNN function. All right, getting a little bit stronger now. If feature selectivity is necessary to maximize test accuracy, ablating feature selective single neurons should cause a decrease in test accuracy. This is a lot better. It's definitely falsifiable. It addresses causality. Necessary is a much more concrete statement than important, and it leads to a specific experiment to test this hypothesis, that we're going to ablate these neurons and we're going to see how the test accuracy changes. Still some problems though, even though this is a lot better. It doesn't discuss alternative possibilities. What happens if we don't see that? What can we learn from that? Is this experiment useful no matter what happens, or is this experiment only useful if we see one particular outcome? There's also no discussion of the baseline here. What's the null hypothesis? What if ablating all individual neurons causes a decrease in test accuracy? That if I ablate any individual neuron, I'm going to get a decrease in test accuracy. Well, does that satisfy this hypothesis? I mean, I would see that ablating feature selective single neurons would cause a decrease in test accuracy, but it wouldn't necessarily be because those neurons are feature selective. It could just be because ablating any neuron causes a decrease in test accuracy. So we need to have some baseline or reference for comparison to understand and contextualize how these results matter. Okay, now we're going to jump to a very strong hypothesis and, unfortunately, a much, much longer hypothesis. If feature selectivity in single neurons is necessary to maximize test accuracy, then ablating those selected neurons should cause a decrease in accuracy proportional to the strength of the neuron's feature selectivity. Alternatively, if networks rely more on feature selectivity across neurons than in individual neurons, zeroing out activity in feature selective directions or linear combinations of units that are not axis aligned should cause a decrease in accuracy that is proportional to the strength of feature selectivity and exceeds that decrease from just ablating single units. Whew. Okay, that was long. So, pros. It's falsifiable. It's definitely falsifiable. It's really concrete. It makes clear testable predictions. It's very clear what each of those statements are. The statements are refined and narrow to specific experiments and specific statements, which is really useful. It presents multiple competing hypotheses. Right? We have an alternatively in there. So what else might we expect? And what could we conclude if we see a different outcome in this experiment? And critically, it provides a nice baseline comparison. We're going to compare single units to the non-axis aligned linear combinations of units. That's a clear thing that we can measure. That gives us a frame of reference about whether a number that we pull out here, that performance dropped by 1%, that gives us some frame of reference of saying, is that a meaningful drop or is that not meaningful? And the main con here, and I would say most strong hypotheses, is that it's verbose. When you write strong hypotheses, they tend to get very long. They tend to get very detailed because in order for a hypothesis to be strong, it has to be clear, it has to be testable, it has to be falsifiable, it has to have competing hypotheses, it has to do all these sorts of things, which means they tend to be long. Key takeaways of this talk that I'd like you to remember, if you remember nothing else, just remember this slide. Intuition is absolutely critical. But we need to be wary of unverified intuition, especially in the context of interpretability. I don't want anyone to misunderstand this talk to mean that I'm saying that intuition is a bad thing or that we should be avoiding intuition. Intuition is really important. The first step in developing any hypothesis is starting with an intuition for how a system is working or what might be happening. We have to develop intuition, but we can't stop there. We have to keep on going a little bit farther every time, and immediately after that intuition, we need to turn that into a clear hypothesis that's falsifiable and that we can test. And that leads into kind of the key recommendations of how we should move forward to build more falsifiability into our interpretability research. The first one is going to be obvious if you've been watching the talk. Make clear, specific, testable, and there's that word again, falsifiable hypotheses. Make sure that whatever your hypothesis is, start with that hypothesis and make sure that your experiment could have invalidated that hypothesis. Make sure that there is a way that could have happened. If not, your experiment is not falsifiable. Be wary of visualization. One's skepticism should be proportional to the feeling of intuitiveness. If something feels really intuitive, you might be falling prey to confirmation bias. Whenever you feel like something is really intuitive, take a step back and say, okay, do I have some quantitative evidence that I can really use to back this up? Or does it just feel right because it matches what I would expect how this model would perform as a human? And that leads into the next one, which is to quantify wherever you can. An unquantifiable hypothesis risks being an unfalsifiable hypothesis, so you want to make sure you can quantify. And this isn't to say that visualization is a bad thing or that you shouldn't include visualization. Absolutely, visualization can be great, but every visualization should have a quantification immediately following it. And finally, remember the human in a human explainability. If a method is aiming to help humans understand DNNs, explicitly test this. Design an experiment like the ones we discussed where you present humans with your method along with other information and show and test whether or not that information helps humans to better make predictions about the networks they're interacting with. And with that, I'll say thank you again to the organizers and most importantly to Matthew for all the help with this research and for putting this position paper and talk together. And if you're interested in more details and references, see the paper on arXiv, and there's a nice QR code there to help you get to it. Thank you so much for your attention.